Welcome to Building with Naz. In today's video, I'm going to go over the REPL terminal async crate, which actually I just published to crates.io I think yesterday or day before yesterday. In this channel, actually, recorded a couple of live coding videos where I've essentially recorded different phases of the development process, actually over the last month or so. So those are, if you look at the channel, there's a playlist here which actually covers some of them. So this is the finished product, so to speak. The not just the sort of the bits and pieces that you've seen built over the last couple of videos, but actually the thing finally, let's say, completed for now, and then published to crates.io. So just as a sort of overview of what this thing is, it's a crate that allows you to build interactive command line interface applications, which are asynchronous and non-blocking. Essentially, it's a drop-in replacement for, well, not exactly drop-in, it's a replacement for readline. And if you wanted to create asynchronous REPLs, read, execute, print loops, where you wanted the ability to create as many Tokio tasks that you wanted and have them concurrently write to standard out, then this is the this is the crate for you. Additionally, it also has a spinner. So let me actually show you real quick what this looks like. So if we see, this is the example, the most basic one. So here you can see, like, if you press up and down, left, right, control left, control right, these are all things that allow you to edit this multi-line editor. It's actually a single line editor that wraps around the terminal. So it appears to be a multi-line editor. So you can do things like, if you hit up and down, this is activating the history function. So you can say start task 1, then you can say start task 2, and then as you can see, output is happening, and this line editor is still interactive. So I can control left, control right. There's a whole host of keyboard shortcuts that work in here, but the point is that I'm navigating my way, editing this content, and while I'm editing, a whole bunch of output is happening in other tasks which have been running this entire time, and it's not clobbering the read line. So this prompt is still good. So I can do info, and then you can see, like, I actually wrote a little program to just show this in action. This tree command just looks through the current directory and then prints all the subfolders and the subfolders in this kind of like tree formatted output, like the kind of like a really simplistic tree command, like in Linux. And then there's also the spinner function, which allows essentially all the output to be paused. And then while it's paused, it shows this spinner. I don't know if you saw that. It was like a animated spinner with a whole lot of color animations. And then, but while the spinner is running, the output is stopped, paused, and then, but all the tasks that had been generating the output, they're still generating, and so all that output gets queued, and then when the terminal is resumed or unpaused, all the pending output is displayed to the output, the terminal. So that's essentially the demo. There's another example for the spinner. So here you can see all the different kinds of spinners and the animations, and this is meant to show like tasks in the background that have been generating output while the spinner is active. So roughly, that's what the crate does. And so essentially, like in this playlist, you can see all the way through the journey, like from the inception all the way to like creating tests and implementing some of the more interesting features. I kind of documented parts of the journey, but not all of it. So in today's video, I'm going to go through the state of the code base as it is right now with all the super cool features that already got put in place, and some of the things that had to change because I ran into some interesting issues with async in Rust. And these aren't like unknown issues, but they are definitely issues that aren't so talked about. So for example, safe cancellation is a thing that came up, which required me to make some changes between this. Actually, there's a release that I did earlier today where I ended up removing a whole lot of essentially all uses of the Tokio mutex and replaced it with the standard libraries mutex because there's some interesting behaviors that happen when you use a Tokio mutex and you hold basically every time you call await and you hold the lock. Interesting things happen uh, in the lock that they don't match up what the standard mutex does. So and I'll go over that in detail later. And I also have videos that I'll share, which go into tremendous amount of detail around like what exactly is going on and what didn't work. So yeah, the summary is something to do with cancel safe and Tokio mutexes, or just async code in general. So let's see. Let me quickly then, before I get into the code, let's actually build the simplest application we can imagine with this crate. So if you look at the examples, they actually provide a pretty good. So if you want, you can look at the. Oh, by the way, this repo is the REPL open core repo. So if you clone the repo, and if you go to the terminal async directory, so this one, terminal async directory, that's where this crate is located. So the REPL open core repo is a monorepo, and it has a lot of different crates in it, and this is one of them. So if we look at the examples inside here, where is the examples? Wow, too many folders. There it is. So if we look at the examples, this is the terminal underscore async example, but it's kind of complicated. So I just wanted to start with like something even more simplistic than this. Like this is a bit complicated. So let's do this the simplest sort of expression of what we can build with this terminal async crate here. So the use case is that I need to build some sort of an interactive command line application. It's not a one-shot, one-run kind of an application, but I want the application to start, and I want it to keep running and I want to be able to give it commands, and then when I give it commands, I want it to produce output. And until I explicitly exit this application, I want it to keep running. So that's what we're going to do here. And because of the long-running nature of this this application, that's where cancellation, handling life cycles, it becomes a little bit more complicated than just a simple application which just runs for a short amount of time and then exits. So that's why this crate really helps you build interactive command line interface applications. So for example, if you do sudo apt remove, let's see, yeah, Ubuntu Pro Client, like this is not interactive. I mean, it is very basic interaction because I can just say yes or no, and if I don't say yes or no, this main thread is blocked, and the apt program process is pretty much stopped. So if I can control C out of it, I can press N or I can press yes. So if I say yen, if I press N and then hit enter, so basically nothing happens until I hit enter because of the nature of readline. This is the standard libraries readline function that's blocking. So essentially, this is not the type of interface that we want. We want a more interactive experience, similar to what you saw in that terminal async example. So let us do this. Let's go to a different directory to get this going. So let's do, let's see, and let's do this. Let's make a new crate. That's right, async CLI. Then in async CLI, we're going to do cargo add rebel terminal async because that's this crate. This one. Actually, here's the source code for that crate. Then the next thing we need, because This is an asynchronous application. We need Tokio. I'm going to add the full features. And then let's add Miet, because I really like Miet for error handling. I'm going to do a separate video on Tokio tracing, on Miet error handling, and a whole host of other really interesting things for async programming. But that's not in this live coding video though. So let's see. So now let us do this. Let's just open this in VS Code. Here we go. All right, so we have a main function, and let us make some, okay, make the fonts a little bit bigger. Let's see, is that big enough? Yes. So the first thing, actually, so if we run it, if we say cargo run it, let's see what happens. Wow. Still compiling. Okay, hello world, yay. So we can say cargo run -q, and there we go, hello world here. So hello world, wonderful. So now what we want to do is let's create a new terminal async. So basically this terminal, maybe terminal async variable will hold this terminal async struct, and I think we do try new. Yeah, so as you can see, there's nice documentation and stuff. So it goes create a new instance of terminal async. Example of prompt is greater than, and it says like if the terminal is not fully interactive, then this will basically just return a none. So we have to be careful about that. So we say try new, and I think the prompt we can just say nothing creative there. So now we have to say let's do this. So we can say let's do a couple of things. Let's make this async main, and then let's do this Tokio main. Okay. So this one, try new. It's async, so we have to await it. And then what we can do is bail if let's see, it's doing two. That makes sense. Sorry. So this one should return a yet result of nothing, and then we can just say this, and then we can put a question mark. There we go. And then here we can say if the let's just basically we're going to assert that in this particular example that this terminal is going to be interactive, and so this will always return some, not none, because this is just a simple example. In this is a non-recoverable error, so there are situations when this code will not work. So if it can't put the terminal to raw mode or get the terminal size, that's not a recoverable error, and it will error out with this question mark. But if the terminal is uninteractive, then this will return none. So the thinking there is that if you're running it in a CI/CD environment, the terminal can be uninteractive. So that's not necessarily an unrecoverable error or like an error case. But if you're trying to put a terminal into raw mode and it won't go into raw mode, or you can't get the size of a terminal, something has gone horribly wrong, and it won't even display output. So there's no point in proceeding. So that's why it basically bails. It's arguable that this might also be like you can't really proceed if this is none. But anyway, that's the design as it stands right now. But if that doesn't work so well, you know, I'm open to changing it. So then let's do this. Let's set up tracing, because that's one of the nice things that you get for free in this particular crate. And here we're just gonna basically do this. We're gonna say tracing config, and from taste tracing config we do new, and we can do, let's see, so it's asking for standard out. So if we look at this, it goes, you need to give, it takes an optional shared writer, and here we can get a shared writer basically. So we can say get shared writer from this one. We can say clone shared writer, and then we can just pass it in there. Let's see, is this init? Let's see, init, that's the config, is this? And, oh, I see, it's expecting some, and finally we give it this config. And then I think, what is this saying? Oh, right. So I think it's, yeah, it returns the result. So if it errors out, then we error out. So this is just setting up tracing. And then what we can do is let's print some, like just to see that it's working, async. We say print, and then let's say welcome to your async REPL, and press Control D or Control C to exit. So basically, there we go. This is actually not far from the truth, so I'm just going to delete this. Copilot was not too bad. What is this complete? Oh, I see. This is saying that this needs to be mutable. All right, so what is this saying? Oh, this is an async function? Oh, okay, so we have to await it. And then I think that's pretty much it. Yeah, it doesn't return anything. So let's run this and see if it works. So it goes info, thread ID, and then it just kind of exited. So we didn't even get a chance to see this async print line work. So let's do this. One way to do this is kind of, you can this is not necessarily the best idea, but you can do something like what is this, sleep? It had it there. Oh, is that not a thing? Oh, there we go. So this is just so we can see the, there it is. Welcome to your async REPL. Press Control D or Control C to exit, and then you see the prompt. And then just this exits after 1 second. So at least we got this far. So far, so good. So I'm going to remove this because we don't need this anymore. So here I'm going to do a loop, infinite loop. And in that infinite loop, what I'm going to do is I'm going to check to see if I can get, actually that's pretty good, where if I can get the, let's see, it's called get readline event. So this is readline event, and what we can do is print this readline event to let's see, format, and then we can do event. Oops, maybe too many. Oh, let's do this. And then we can put that here. Okay, so let's run this and see what happens. So it's not liking it. Oh yeah, right, because it's an infinite loop. So this will just loop forever, and that's, well, what we can do is we can check to see if it's Control C. So we can say something like, we can say match. Yeah, if it's Control, oops, say, oh, that's right. It's Control C, Control D is end off. This is and this is not control C, it is interrupted, this one. Actually, since we're in here, might as well flesh this out, right? So we can do, let's see, we're gonna replace, actually, let me just bring in this one. Okay, so here we can say line. So this is the readline event line, and that's actually correct. So we don't need this anymore. So basically what's happening here is that if you press Control D, it breaks out of the loop, Control C breaks out of the loop, and if you actually type something, it'll simply type output whatever you typed, right? It'll echo it basically. So we can say, that's exactly right. There we go. And then let's see if this works. Ah, there we go. So this is a very simplistic kind of expression of this program, or the very simplistic use of this crate. So this is basically the simplest program we can write. Then there's other ways to do more interesting things like using the spinners and such. But for that, you know, there's a really nice example, which is this one. I would recommend going through that. So there we go. We built out, and that was Control D, and then when I hit Control C, so let's do this. Let's instead of just saying break, let's just do this. We can say, let's say Control D exiting, and here we can say, let's see, oops. We can say terminal Control C exiting. That's exactly right. Use info, help, hello. So these are, it's just echoing it right back. So when I hit Control C, there it is. And I hit and then Control D, there it is. And also, instead of doing terminal async print line, I can just do info. Basically, this is Tokio tracing. Why isn't it pulling in Tokio tracing? Oh, I don't think I imported it in cargo toml. Okay, so if I, yeah, I didn't bring it in. Let me see. Let's bring it in. Say cargo toml for, let's see if we wanted to do Tokio async, I'm sorry, Tokio tracing, where is it? Here it is. So let's bring all these in to cargo toml. So we can do, there we go. So now we should have info. Yep, there we go. So I just wanted to show you this. Let's take out the Control D and then let's replace this with, the reason I'm showing this is because we set up this Tokio tracing thing for use with this this crate, and that's one of the nice features of it. So you can say like Control D. Oh, so it never got a chance to because it just quit. So what we'll do is just, this is a made up nonsense demo, so we'll just put a wait at the very end so that things can kind of flush and clear out. So here we see Control C, there we go. And we can do Control D, and there we go. And 1 second is way too long, so we can say from milliseconds, maybe we can do 10 milliseconds. That might be a more reasonable delay. There you go. So hit Control D, and you see that info message. You hit Control C, you see that message. And if you don't, and if you just say hi, hello, Control C, and then hi, hello, Control D. So that's essentially it. And of course, you can do anything, make your own processing engine so that you can take this line, this string, and then parse it and do all kinds of things that you need for this particular interactive experience to work. So, so with that, let's switch back to the source code that I wanted to walk you through, just to give a sense of like what else what else has been done in this crate to make it release ready. So one thing I did was in lib.rs, I generated quite a bit of documentation. This was not there at the start, but it kind of goes through like the mental model at a high level that describes like how you think about this crate, how would you use it, but it doesn't go into like how things are implemented. It's more like for you to understand at a high level, just to grok the mental model, and then kind of like you have certain intentions. Do those intentions match up with this crate? And if they do, then how do you express those intentions? That's basically what's going on here. For deep dive into what each one of these this crate actually does, like the main structs that you or files you want to look at are readline and spinner. And if you wanted to look into tracing, there's also tracing. So basically you can jump, these are jumping points. And of course here's the YouTube videos. So basically this is what it looks like once it's all put together. So we have the nice description of what it does. This is a librs, but nicely formatted on crates.io. And this is actually looks even better on docs.rs, which is really where it's intended to be. So this is, you know, that lib.rs file, just really nicely formatted, and so you can see like all the stuff in here. So this is one of the I think things that are really important for crates is that just to put in that extra effort and polish so that there's decent documentation, but not over documentation, because it's like there's a balance between like repeating yourself, like so for example, if there's certain information that's scoped to readline, then it's better served for that to remain in readline rather than librs, because now it's just duplicated. And also the scopes are mixed, meaning that the scope for this particular librs is to provide high-level mental model, sort of an outline, not the nitty-gritty of how it's done. Okay, so there's a couple of interesting things to look at in this code. The first thing I'm going to walk you through is the life cycles, because I had mentioned something about safe cancellation. So this is safe cancellation. So essentially, I'm going to put a link to this video in the description. It's by Steve Klabnik. It's really good. At 34 minutes or so, he does great justice to what exactly is going on and why there's been an issue, or there can be an issue. And so this is exactly the kind of thing that I ran into and had to work around. So in a normal standard libraries mutex, which is not async, when you lock it, it stays locked, and then a certain number in the code in your critical section executes, and then you unlock it. In the async version, when you say lock.await, then the problem is that because of how Rust async and await works, essentially it doesn't work the way synchronous code works. So in between the call to this await and that await, this lock, the contents of the lock are actually are lost. So that's pretty awful. And so there are situations where this will produce an error. It's not every time, but sometimes. And so to avoid it completely, one thing, and please do, I'm purposefully not going over the details. Like if you're curious about the details, the commit, there's actually a tag, a release tag 0.4.0, which talks about this in quite a bit of detail. And I'll put a link to this in the description as well. So, and even in the Tokio documentation, it goes into a copious amount of details and explaining like what you should use. And roughly the direction from Tokio is just to use this ordinary mutex in asynchronous code. So if you're going to do an arc mutex, instead of doing an arc Tokio mutex, just do an arc standard STD mutex. And so in this in the code base, everywhere a mutex is used, I just created a type alias called std mutex, and then there's a whole bunch of objects that need to be passed around between different functions, and also tasks. And so actually different structs need to be passed around, and so those tend to be wrapped in an arc std mutex. And so this is pretty consistent. Like std mutex is literally used everywhere, and there's no Tokio mutex. And I did that just to be explicit, just so that it's kind of like clear that, okay, this is not async. This is actually the regular sync mutex, even though it's being used in asynchronous functions and in sent between tasks. So so that's one sort of thing to make note of. And where you can see this used is let's see. So there's a new associated function, which is under the hood. It's how everything gets started. You have to create a new readline. That sample program we made where we said try new, under the hood this goes and calls new, readline new. And here it creates a bunch of these arc and then standard mutex, and then it wraps some type. And then those get put in this readline struct. And then as various other tasks need access to them, these can be safely passed to those tasks, because they're safe to send across different tasks. So, and one of the things that happens is when readline starts up in the new associated function. This is another kind of common pattern with async Rust, is when you're creating long-running processes, there's this task that's immediately spawned. So when new runs, it sets up a bunch of structs, sets up a bunch of data structures in memory, and then wraps them in arc mutex, std mutex. And then it spawns a task. And this task, basically what it does is that it monitors a Tokio broadcast channel to see if it should shut down or not. And the beauty of this broadcast channel is that it's safe to send between tasks. So you can just clone it and send it, across however many tasks. And if in those tasks you have some loop, some sort of event loop, you can do something like this. You can say Tokio select, and then you can put. So the cool thing with the broadcast channel is that once you, so let's go look at where this was made. So where it was made is here, shutdown channel. So it goes let shutdown channel, and then it goes and makes itself a broadcast channel, which is generic over bool, and of capacity 1, because it only will be used the one time. So capacity 1 makes sense, because as soon as somebody sends any bool, true or false, it'll trigger all the receivers of this channel. So what you do is you get the sender out of it, and then that sender now can be cloned any number of times. And even though I'm sending that sender to a different task, see, Tokio spawn, and I'm moving, right? What I do is I grab the receiver from the sender, which is pretty cool. You can say shutdown sender.subscribe. This is a Tokio thing, and it'll give you a receiver. So this makes it effortless just to clone these senders and spread them throughout your code. And then you can put a select statement or macro around the receiver, and then when anybody in your code base, let's say in this program, sends a true or false, it will cause this this branch to. So basically, Tokio select erases these two futures, and so as soon as somebody sends a true or false, the receiver, this branch will execute and it will break out of the loop. So that's essentially all it does. And so if you look at all the places where this is used, you will find, like, here's an example. Where is it? Shutdown sender. There we go. So as you can see, it's also used in this readline function. And this readline function is the thing that gets called when I jumped to the simple example that we made at the start of this video. So when you say terminal async.get readline event, under the hood, this turns around and calls readline. So that's how that happens. And so in this readline, you'll notice that it just grabs the receiver end of the shutdown channel, and then it puts it in an infinite loop, which is basically racing these futures. And as soon as somebody sends a true or false in the shutdown channel, the receiver will be triggered, and in this case, it breaks with an error. So this is roughly like how in asynchronous code with really long lifespans, like the life cycle kind of goes on for a while, because once you, like when we initiate this program, cargo run, when we run this program, like notice it's still running, like it's still going, right? So it's still responding to my key presses and so on. So this could go on for a while until I press Control-C or Control-D. And so when I press Control-C or Control-D, this shutdown channel is used to essentially gracefully and cooperatively exit all of the tasks that may be waiting or executing. So if they're executing, then the next time they go, they finish whatever asynchronous code they're running right now, and the next time an await point is hit, then essentially this code path will execute, and then the break will execute. So this is a graceful way to shut down. The other way is you can abort the task, but that I got mixed results with that, because it doesn't always work the way one might expect. So it's not a very clean way to do things. This works really well, and yeah, please check out this video and take a read on the Tokio docs, and it essentially supports this sort of approach. So that was the cancel safe or cancellation safe async mechanisms, and the use of the shutdown channel to make that happen. So two things: using a standard mutex, so arc, standard mutex, and then your type, even for async code, and then the second is shutdown channel, the using a Tokio broadcast channel that you can use to very cleanly, repeatably, reliably shut down all the different tasks that constitute your running program. And it's trivial to take the sender and clone it and send it around. The last thing I want to cover is a bit of a Rust type system deep dive, and I intend to do a separate video on this, but I kind of wanted to touch upon it. So initially, when I built the readline, and let's go to the new. So when you call the constructor, you would have to pass a prompt, and then you would just have to pass standard out. And here, you wouldn't have to pass anything. And what it would do is that it would just use something called the cross terms event stream, which is basically something that comes out of cross term. It's this one. Let's look at cross term event stream, this thing. And it would basically get up, down, all the key presses from your OS, and then it would supply them to your program or whatever program is using this as an async stream. So in order to make this code reusable and testable, and also to give it the ability to integrate with a whole host of other systems that are not just standard in, standard out, standard error, I ended up creating this interface where you tell it something, you give it a thing that's what the safe raw term is. It's something that implements the write trait and the send trait. So it's dying standard IO write and send, so it has to be write and send. And then it's wrapped around in a standard mutex, which is wrapped in an arc. So it's safe to clone and send it between tasks and threads. So that's the, so essentially you could pass, if you look at some of the tests here, where is this? The tests are down below. So you can see that I can mock standard out basically. So I don't necessarily have to provide a real standard out. I can actually mock it. I can provide a real standard out, but I can also provide a mocked standard out. So that's kind of like one of the cool things with this abstraction is that so here's an example. So when it's used in practice, what happens is that the an event stream is created, it's pinned and boxed, and then that gets sent or moved into this readline struct, which is really cool. So this way I can use the actual cross-term event stream. But if I want to, let's say, mock it in a test, then what I can do is I can just, here's an example. I can create my own standard out mock, which essentially implements, it's a struct that just implements write. Remember, it has to be send and write. So it implements it implements write, and what it contains is something that is send, because arc standard mutex vec of u8 is actually send. So this thing satisfies the trait bounds that are set forth here. So that's really cool. And so whether I'm using let's say let's go look at the new. So if you just search for usages for the new function, you'll see it. So whether I'm using box pin event stream or I'm using arc standard mutex new and then a mocked up standard out, like it works. So oh, I'm sorry, I'm comparing two different things. So sorry. This one was the event stream is sorry. I compared the two. So in this example, like in the terminal async rs, the pinned input stream is let me unwrap this a little bit. So the first argument is the prompt, which is fine. The second argument is this standard. It's this thing. It's the it's any type that is write and send. That's this thing. And so we can see here, it's standard. It's basically the standard out from the standard library, wrapped in a standard mutex, wrapped in an arc. That's what we pass in here. And in the tests, what I was showing you is that the same standard out, I can mock it using the struct that I made up, which is also write and send. So this is an example of the first argument to new that I can use something real, which is the actual standard out, or I can make it up and just use like a mock. But there's other reasons for doing this, because I do intend to integrate this with the REPL TUI crate, and the REPL TUI has its own way of providing like an output target for a component to render. So using this sort of abstraction, I can sort of abstract away standard out to anything. Similarly, if you look at this example again, the second argument to readline, which is pinned input stream, This thing can either take a real event stream, which is pinned and boxed. That's one approach. Another approach is that I can fake it. So in tests, I have, let's see, where is this? I have this function called generate input stream, and it actually generates a pinned input stream. And I just make up my own made up stream. And basically what I do is I just have some hard-coded values, and I just make sure that when somebody uses made up input stream, that it will always press A, then press B, then press C, and then press enter. And then I just return a box pin. I just box and pin that the async stream that's returned by this macro. So that is really, really cool. So that was super, super handy in being able to test both the input and the output. So the input, so if you look at the essentially this first this safe raw terminal thing is the output device, and the pinned input stream is the input device. So essentially now I can wire this into REPL TUI. I can wire it into a test fixture. It opens up the quite a bit of flexibility in what can be done with this. Because in the past it was essentially hard coding standard out, and it was hard coding event stream, which made it untestable. Because I couldn't fake what was going in, I couldn't fake what was the thing that the output device, and I couldn't fake the input device. So here both the output device and the input device are fakeable because they rely on this this type. So again, this is going to be its own video because there's like a whole universe of stuff that goes into making this work, or just thinking, not really making it work. Like once you figure it out, the expression is relatively straightforward, but like how to thread this through all the different async tasks and all the different functions, that wasn't trivial. So those are essentially some of the things I wanted to cover in this video. So yeah, I think yeah, please give it a try. It's on crates.io, and then I will create more videos talking about like I think I have like a whole host of them. Like I want to do one with trait bounds and polymorphism, and a whole host of others that I touched upon in this particular video. So if you like this style of video, please give it a thumbs up. Please subscribe to my channel, and if you want more content, you'll get notified when I make more videos. And also, if you haven't seen Developer Life, check it out. It's this is the video channel for Developer Life. Developer Life is, I've been running it for decades, and there's a lot of Rust content, like procedural macro guides and things about JetBrains IDEs, like how they're constructed from the ground up and so on. It's just kind of a culmination of all my experience and all the different roles I've had. Like I used to work in Android Studio at Google, the Google Maps API team as well, and a whole host of others. So a lot of interesting stuff in there. At least I think it's interesting. Yeah, so check out developerlife.com, and you can always subscribe for updates. That way, when I drop new content on Developer Life, you'll be notified of it as well. So thank you for watching, and I'll see you in the next one. Have a great day.